For the final exam review on polynomials, we first want to start talking about adding and subtracting polynomials. Then we'll get into basic multiplying and then double distributing and ways to organize that. So first, I want to pay attention to the fact that we have x squared plus 3x minus 1, that whole quantity, plus 4x squared plus 2. And you might be able to just add term by term. Remember, if we want to add terms together, they must be like terms. And in order for something to be a like term, it has to have the same variable and the same exponent. The coefficients can be different, and that's essentially what you add and subtract, keeping the variable part the same. So you might be able to look at these two and say I could just add the like terms and go from there. One way to organize it, though, would be to try and line your terms up vertically. I think that's a really good option. So I'm going to take that first expression, and then I'm going to add, and then I'm going to put the like terms underneath each other. So the second quantity, 4x squared plus 2, I'm going to put the 4x squared under the x squared and the 2 under the minus 1, and then just add vertically. So I should get 5x squared plus 3x plus 1, and then I didn't have to put that much thought into what needs to be added once I line them up vertically. Again, it's not necessary for you to do it that way. I just think it's really helpful, especially when you get into longer expressions. So similarly with number 2, looking at the terms I have there, I want to add those two expressions. So I'm going to line them up vertically. So I'm going to write the first one, and then I'm going to add the second expression by stacking the like terms with each other. If there are terms that don't have a like term, we'll talk about how to do that in the next problem. But right now we have x to the fourth, x squared, and a constant term. All three terms have a like term, so if I just add vertically, I get 3x to the fourth, and then actually I have 3x squared plus negative 3x squared, which is 0x squared. I'm not going to write 0x squared, I'm just going to leave it blank. And then 2 plus 6 is 8, so my final answer is just 3x to the fourth plus 8. Oops, I should say 3x to the fourth. Okay, and then for number 3, we have two expressions being subtracted. Want to handle that slightly differently. So the first thing I like to do is just distribute that minus sign to that second quantity. I think it's just an easier way to deal with what's being subtracted. And then I'm still going to line up my like terms, but I think after I've done that, it's a little bit easier to deal with what's positive and what's negative. So now I'm going to take that first expression, and I'm going to line up the negative 7x with the negative 2x and then negative 10 with the 1. And once I've distributed the negative, we're essentially just adding the two expressions together, because instead of thinking of subtracting, it's really like adding the opposite of the other expression. So when I add vertically, I should get 5x squared minus 9x minus 9. And I'm going to handle that similarly with number 4. First going to distribute the negative, and then I should get 5x cubed plus 2x minus 4, and then that minus distributed through that second quantity leaves me with those three terms, negative 4x cubed, negative 2x squared, positive 5x. And now I'm going to line up my like terms right here. So I have 5x cubed and minus 4x cubed. I'm going to line those up. And then what you'll notice is in that first expression there isn't an x squared, but in the second expression there is an x squared. So what I'll do is just write that minus 2x squared with the second expression. You could have written it up above, it doesn't matter. I'm just trying to keep the first part together and the second part together. But again, there's no x squared in that first expression, so there's nothing to line up vertically. I'm only going to have one term there. And then line up my x terms, and then so 2x and 5x, and then I have a minus 4 and no other constant term. So once I've kind of organized this, I just essentially add vertically. So I should get x cubed, and then nothing plus negative 2x squared is negative 2x squared, 2x plus 5x is 7x, and negative 4 plus nothing is negative 4. So it's kind of the way you can handle a subtraction, distribute the negative, and then kind of stack up your like terms. Or just go term by term and make sure you've added or combined all like terms, and anything that doesn't have a like term doesn't obviously get combined with anything. It should be present in your final answer. And now I want to talk about some basic distributing. So we have a number multiplied outside of a few different binomials. So I want to distribute So 5 times 2x minus 3, negative 2 times x plus 4, and 3 times 1 minus 3x. I'm just going to distribute that through. So we should get 10x minus 15, negative 2x minus 8, and positive 3 minus 9x. Once I've distributed, I no longer have any parentheses anywhere. I'm just going to try and combine like terms. So I have 3 different x terms. So I could line them up vertically or not. It's up to you. 10x minus 2x and minus 9x, and then a negative 15, negative 8, positive 3. If I just stack them vertically and add, I should get negative x minus 20. So it should be 10 minus 2 is 8, minus 9 is negative 1x, or just negative x, and then negative 20 for the constant part. Number 6, now I have a single term, a monomial times a trinomial, so I just have to distribute that through that entire quantity, but be sure you handle the exponents carefully. So I have a negative x squared times a negative 2x squared, so negative times a negative is positive, 2 should be the coefficient, and then x squared times x squared is x to the 4th. A negative x squared times a positive x would be negative x cubed, and negative x squared times negative 3 would be positive 3x squared. None of those are like terms, so nothing can be combined, and that would be your final answer. And then for number 7, we're going to still talking about distributing, but now we have a binomial times a binomial, and there's really two major ways to organize and complete this problem. You can either just distribute by drawing arrows, or another way to organize it would be to draw kind of a box as a reference to keep track of your multiplying. That's a strategy that I've shown, a strategy that is really nice if you can carefully make sure you're multiplying correctly. So if I wanted to do that, I'm going to show both ways for this first one, and then kind of mix and match the way that I show it for each one depending. So I'm going to show both ways. If I just want to draw the arrows, I would just go term by term. So 9x times 9x is 81x squared. 9x times minus 2 is minus 18x. Positive 2 times 9x is positive 18x, and positive 2 times negative 2 is negative 4. So those 4 terms are what you get when you multiply, and then all you have to do is check for like terms, combine anything, and you'd have your final answer. So notice in the middle there, negative 18x and positive 18x are like terms, and they add to 0, so what you're left with is 81x squared minus 4. So that would be just foiling is what it's called sometimes, or just double distributing. Another way you could do it is to draw a box. So if I have a binomial times a binomial, I should have a 2 by 2 box. And then write each binomial on the edges of the box, one across the top, one across the side, and then multiply the 2 parts that make up the edges of the box to fill it in. So what I mean by that is 9x times 9x is 81x squared. That goes in the first box. And then 9x times positive 2 goes there, which is positive 18x. And then negative 2 times 9x is negative 18x, and negative 2 times 2 is negative 4. What you'll notice is, what I like to do here is take those 4 terms and just write them in line with each other. You'll notice those are the same 4 terms as we got previously. So combine the like terms the same way, you should still end up with 81x squared minus 4. So those are 2 ways to organize your multiplying. Both are viable options. You kind of pick which one works for you. I'll show one or the other as we work through, kind of showing both, just so you're comfortable with the method that you prefer. So number 8, a binomial times a binomial again. I'm going to make a box for this one. Still double distributing or foiling. It's just a nice clean way to keep track of what needs to be multiplied. So one binomial along the top, one along the side, multiply to fill in each box. So the first box should be 25x squared. 5 times negative 4x is negative 20x. Be careful with your positives and negatives, because what they end up becoming are minuses and pluses when you write your expression back as a polynomial. So it does definitely matter. So positive 4 times positive 5x is plus 20x, and then plus 4 times minus 4 is minus 16. And then I like to take those and write them as a single expression and then see what combines. The middle terms in this case actually add to 0 again. So what I'm left with is 25x squared minus 16. Now what you'll notice is the middle term drops out, and if you look at the structure of the binomials, they're the same binomial except for the sign in the middle. One's plus, one's minus. Same thing happened with number 7. So when we have a binomial that differs by the sign in the middle, what happens is you end up with a difference of two squares. So notice 81x squared in number 7 is perfect square and 4 is a perfect square, and same thing happens in 8. That'll matter a little bit when we talk about factoring, but that's why that expression 25x squared minus 16 would factor into 5x plus 4, 5x minus 4, because it makes that middle term drop out. Now the difference between those and number 9 is actually a binomial multiplied by itself. So what should happen is the middle term shouldn't drop out. It would actually combine into something, which you'll see here in a second. So the first step I would do is definitely make sure I write it twice. The tendency we have to do here is just to square x and square 14. That does not work because you totally miss out on the middle part of this polynomial. So you'll see that. Again, you can just draw the arrows, or you can draw a box. So if I just went the old school distributing way, x times x is x squared, x times minus 14 is minus 14x, minus 14 times x is minus 14x, and negative 14 times negative 14 is 196. So 4 terms still, 2 by 2 multiplies to 4 terms. Some may combine into less terms, maybe, maybe not, but at least should have 4 before you combine anything. And then notice the middle, they combine, but they don't cancel out. I have negative 14 minus 14, which is negative 28. So instead of the middle term adding to 0, the middle term actually doubles because it's the same term twice. So this x squared minus 28x plus 196 is the multiplied out version of that x minus 14, which is why we call x squared minus 28x plus 196, the term for that is what we call a perfect square trinomial, because the first and last terms are perfect squares, and the middle term is double the square root of the last term. Not that you need to memorize that, but you'll see how that structure reverses itself when we talk about factoring a little bit later. Number 10, again, I have a repeated binomial, so the first thing I would do is write that binomial twice, and then I'm going to multiply it out using either a box or drawing the arrows and distributing. So this one I'm going to make a box. I'm just trying to alternate the method so we see a good amount of both. So I'm going to write one factor across the top and one binomial factor across the side, and then multiply to fill in the boxes. So 3x times 3x is 9x squared. 3x times positive 5 is plus 15x. Positive 5 times 3x is plus 15x, and positive 5 times positive 5 is positive 25. And then again, what I like to do at this point is just write all 4 terms in a row or in a single polynomial expression, and then see what can be combined. In this case, the 2 middle terms add to 30x, and I'd be left with 9x squared plus 30x plus 25. Number 11, it's not the same binomial twice, or the binomial differing by plus or minus, just 2 distinct factors. But I'm still going to double distribute whichever method I'm most comfortable with. This one I'm going to draw the arrows here. So 3x times 2x is 6x squared plus 9x. And then I multiply that minus 5 times that second quantity, which would be minus 10x and minus 15. And then I look to see if I have any like terms at all. In this case I do. The positive 9x minus 10x, those combine to minus 1 or just minus x. And then my final answer should be 6x squared minus x minus 15. If I were to try and factor that answer, I should factor right back into those 2 binomials. That's why distributing and factoring are reverse processes or reverse operations of one another. Number 12, still a binomial times a binomial. In this case, I'll make a box. It doesn't matter which one you put across the top or across the side, because you're going to end up multiplying everything anyway. So filling in the box, you should get 3x squared and plus 6x across the top, and then plus 5x, and then plus 10. Then I'm going to write all 4 terms out in order, and then see if any of those terms combine. So the positive 6x, positive 5x in the middle adds to positive 11x. My final answer is 3x squared plus 11x plus 10. Number 13, still multiplying. In this case, though, we're multiplying a binomial times a trinomial. So I could draw the distributing arrows and go from there, and it should work. The only problem with that is it tends to be a little bit tricky to keep track of all of your terms. So one thing I like to do is either make a box for it, The only difference is I'd make a 2 by 3. So in this case, I'm going to make a 2 by 3 box. So it looks something like that. And this, it does matter which one goes where. X minus 6 is the binomial, so that should go on the side with 2 boxes. So I put that one there, and then 4x squared plus 3x minus 5 goes across the top. Again, with the 2 by 2, it won't matter here. It only matters because if I tried to put 4x squared plus 3x minus 5 on the side, I wouldn't have enough boxes. I want one box for each term. And then I just multiply and fill in each box. So I should get 4x cubed there. Be careful. X times 4x squared is 4x cubed. X times positive 3x is positive 3x squared. X times minus 5 is minus 5x. So that's the x being multiplied by all three of those, which would be the same thing if I took x and distributed it through that trinomial. And then I have to multiply everything by minus 6. So minus 6 times 4x squared is minus 24x squared. Minus 6 times 3x is negative 18x. And negative 6 times negative 5 is positive 30. And then I like to, again, just take each term and write it out in order. 4x cubed plus 3x squared minus 5x. And then I could go ahead and just write the next string of digits. But one thing I do when I have more than 3 or 4 terms is I try and start to line them up vertically. I think it's a helpful way to add, but it's definitely not necessary. So what I would do here is take that negative 24x squared and actually put it underneath my x squared, and then put my minus 18x underneath my minus 5x, and then plus 30. And what I've done is vertically aligned my like terms. So all I would need to do is add, and I should get these totally simplified expression. So 4x cubed minus 21x squared minus 23x plus 30. You don't have to line them up like that or stack them. You could just write one long string and add and subtract. That's the same thing I did. It's just a little bit easier when you start to put them one underneath the other. In 14, I'm going to multiply, obviously a trinomial times a binomial. It's the same problem as number 13 in terms of its concept, just the trinomial is written first. So I can just distribute here, so I'm going to do that. So I'm going to I always take the smaller one and multiply it to the larger one. I think it's easier to keep track of. So I'm going to do x times 4x cubed, which is 4x to the 4th. X times minus 6 is minus 6x squared. And x times plus 7 is plus 7x. And then I'm going to take that plus 1 and distribute it through there. And I should get plus 4x cubed minus 6x plus 7. And now here I'm looking for like terms. Let's see if I have any like terms at all. And I have an x to the 4th, an x to the 3rd, an x squared. Here I have two x's. So I'm going to write my answer in standard form. So I have my 4x to the 4th plus 4x cubed minus 6x squared. And then I have 7x minus 6x, which adds to positive x, and then plus 7. And there would be my final answer for that distributing. And now that we've talked about multiplying a binomial times a binomial, distributing a trinomial times a binomial, the next part of polynomials, the huge major part of polynomials we need to talk about, is factoring. And factoring is essentially the process of taking an expression and rewriting it as a product of its factors. So that can mean a lot of different things. Could mean just taking out a greatest common factor. It could mean taking a quadratic and factoring it into two binomials. It just depends on the structure of the expression, but the idea of factoring is, the way I like to explain it is, it's essentially reversing what is a distributing process. So if you look at number 15, x squared minus 44, and we think about the different factoring methods, or kind of the factoring trajectory we talked about, always look for a greatest common factor. And if there is a greatest common factor, you would factor that out. Now, if there's not, really the next check is, am I dealing with a binomial or am I dealing with a trinomial for our factoring purposes? And they do factor slightly differently. So if you look at number 15, we're dealing with a binomial. And so the check would be is, if there's no greatest common factor and it's a binomial, if it factors, it would need to be a difference of two squares, meaning both terms are perfect squares with a subtraction in between. And in this case, we have that. X squared is a perfect square, and so is 144. So a difference of two squares factors in a very specific way. It will factor into two binomials, and each binomial will be made up of essentially the square root of each term. So the first term in each binomial comes from x squared, which is x and x. The second term in each binomial comes from 144, which is 12 times 12. That's why it makes it perfect squares. But the particular way that it factors is one of the factors should have a plus between them, one should have a minus. And the reason why it factors that way is, if you remember on the previous page when we were talking about multiplying two binomials together, we saw that x plus 12, x minus 12, if I were to multiply them out, the middle term would actually cancel out, leaving me with just x squared and negative 144. That's why this difference of two squares factors this way. It is different than what we'd call a perfect square trinomial, which we'll get to, but if it's two binomials and you check for greatest common factor, the only way we've talked about factoring them is if it's a difference of two squares. So that's how we would handle it. X plus 12, x minus 12, and you can always check your factoring by redistributing that. If you don't get what you originally started with, then your factors aren't correct. So for number 16, again, is there a greatest common factor? 36 and 25 don't share any numbers that both divide them, and one has an x squared, one doesn't. But since we're dealing with a binomial, we would check if this is what we'd call, again, a difference of squares. So 36 is a perfect square, x squared is a perfect square, and 25 is a perfect square, so we are dealing with a difference of two squares. So if I want to factor that, it'll factor, again, very similarly to the previous one. It'll factor into two binomials. So the binomials would be 6x and 6x. Those multiply to be 36x squared, and 5 and 5. And then one should have a plus in there, one should have a minus. The order of the binomials doesn't matter, but if I multiplied that out, I would go right back to that original binomial that I started with. So that's essentially the structure of a difference of two squares. Now 17, on the surface, doesn't look like the difference of two squares, but again, I first should check for greatest common factor. So 8y squared and 98, the factor that they have in common is actually a 2. So if I factored a 2 out, I would get 4y squared minus 49. And then if you look at that resulting binomial we have, that is a difference of two squares. So thinking about factoring that, in my full factorization, you'll notice the direction said factor completely. That means make sure everything is as factored as possible. I should still have that 2 out there, and then I would build my two binomials from that difference of two squares. So 4y squared would be 2y and 2y, and 49 would be 7 and 7, and one should have a plus and one should have a minus. So again, your final answer has to have that greatest common factor as part of it. Otherwise, if I tried to multiply it all out, I wouldn't be able to go back to my original. So that 2's got to be there, and then the two binomials are almost the same aside from the plus and minus. That's how a difference of two squares factors. Recognizing a difference of two squares at the beginning is really helpful for remembering the structure of how it factors. And then number 18, now we move to a trinomial. And thinking about how this factors, we have to remember our basic pattern or structure of how trinomials factor. So if they factor, they should factor into two binomials. And then what I showed was essentially building the binomials from the structure of the expression, thinking about how it would need to multiply out to get that. So because the first term is x squared, the first term of each binomial is x and x. And then what I'm looking for is factors of 36 that add to negative 12. So two numbers that multiply to be multiply to be positive 36, but add to be negative 12. The only combination that possibly works is negative 6 and negative 6. So it doesn't matter where you put what, they're the same number, and they're both binomials start with x. So if I multiply that out, I should get exactly what I started with in the previous example, and there's really not any work to show other than just writing the binomials from the way the expression is. And then similarly for number 19, we're again looking at a trinomial, first checking if there's a greatest common factor between 9, 42, and 49. Since they don't all have an x in them, I know there's no variable greatest common factor, but do 9, 42, and 49 share any common factors? And the answer is no. So then what I'm looking to do is factor this as two binomials. And what I referenced before is there's really two special cases, what we call a difference of two squares, which is a binomial with perfect squares and a minus between them, and what we call a perfect square trinomial. And what that means is there's three terms. The first term is a perfect square, the last term is a perfect square, and then the middle term is really double the first and last term. Here's what I mean. So if you look at the first term, 9x squared is a perfect square, and 49 is a perfect square. So if I think about making 9x squared, the combination that would work would be basically the square root of 9, which is 3, and the square root of x squared is x, so 3x and 3x. And then what multiplies to be 49 would be 7 and 7. Now the reason why it's called a perfect square trinomial is, if you think about what 3 times 7x is, so if you just multiplied the terms together that are inside one of your binomials, so if I multiplied 3x and 7, I get 21x. So if you take 21x and double it, you get the middle term. That's why it's called a perfect square trinomial. So to decide whether there should be pluses in between there or minuses in between there, both binomials will be exactly the same, but the way you know if it should be a plus between there or minus really depends on the sign right there. So if that was a minus, if that was a minus 42x, the only thing that would change is my binomials would be 3x minus 7, 3x minus 7. So that's why it's called a perfect square trinomial. It is another one of your special cases, but if you don't remember that one, you can basically try your combinations of 3 and 3, or 9 and 1, and 7 and 7, or 49 and 1 until you find the one that works, and it would have to be this one. So your final answer is, again, here's your check, 21x and 21x make 42x. So my final answer would be those two binomials. Number 20, it's got a lot going on. You should hopefully notice there are two different variables. So the first thing I'm going to try is to take out a greatest common factor. 3, 8, and 48 don't have any numerical common factors, but each term has at least one x in it. So if I take an x out, what I'd have is 3x squared minus 8xy plus 48y squared. And then looking at what I have left, although it has two variables in it, you'll notice the first term is x squared, and the last term is y squared, and the middle term is xy. And that's because when I build my binomials, the outside-inside product should make xy in the middle, and I'll show you what I mean. So thinking about this trinomial, if it factors, it'll factor into two binomials. The first term of each binomial would multiply to be the first term of my original expression, so 3x and x. And then I need factors of 48 that would go in, factors of positive 48 that would make the outside-inside add to 8. And the idea there is they have to multiply to be positive, but add to be negative. The only way that's possible is if they're both negative, but thinking about my different combinations, you could try a bunch. There aren't any that would work. So in this case, factor completely just means, again, if I had it be a y, but again, factor completely just means take out an x, because that what's left, that trinomial, doesn't factor. And you could try a few different combinations to get there, and what you'd notice is there isn't one that makes that middle term perfectly, so that would be your factoring, which is just the GCF. 21, now we have a trinomial again. 3x squared, 2x, and negative 1 don't have any factors in common, so first I'm going to look to build my binomials. And because the first term's 3x squared, it can only be 3x and x, right? There are no other factor pairs of 3. And then I'm looking for factors of negative 1 that would make the outside-inside add to 2. So the good news about 1 is it's only 1 and 1. Those are the only factors of 1, and 1's got to be positive, 1's got to be negative. So thinking about why this combination works is if I check the outside product there, that'd be 3x, and the inside product would be negative x, and positive 3x minus x adds to 2x, so that is the middle term I need, and that's why that factorization worked. If I switch those and put 3x plus 1, x minus 1, I wouldn't make the middle term the way I want to, which is why it doesn't factor that way. It factors with 3x minus 1, x plus 1. There is only one answer for factoring into two binomials. It's not like any other combination could work, so you can always check before you move on and make sure that you have the right answer. Okay, 22, I handle it similarly. There are no common factors, so I'm first going to look to build my two binomials. And then 5x squared is made with 5x and x. When the coefficient out front of the x squared is prime, meaning it only has a factor of 1 in itself, it tends to reduce the amount of work that you need. And then 2, I need factors of negative 2 that would make the inside negative 3. So factors of 2 are really 2 and 1. But if I think about where 2 should go and where 1 should go, it has to go like this. It has to be plus 2 minus 1, because my outside would be 5x times negative 1 would be negative 5x. And then my inside would be plus 2x. So if I added those together, I get my middle term, which is what I wanted, which is why that factoring combination is the correct one. So if you're unsure, this outside-inside product that I'm doing will make your middle term. Now the reason why I'm not doing the rest of the distributing is because I know 5x and x multiply to 5x squared, and 2 times negative 1 multiply to my last term. My first term and last term will be made correctly. It's the middle term that really is the tough one to make, so that's why it's always a good idea to check. I'm showing the check. I don't do it myself when I'm doing the work, but I'm just showing it so we can see that we're able to check our answer before we move on. So looking at the next problems here, always going to check for a greatest common factor. If there isn't one, then I'm going to proceed. So if you look at 23, 8x squared minus 8x plus 2, they actually all have a greatest common factor of 2. So I'm going to factor that out first. And then I have to think about how the rest factors. What I mean by the rest is that trinomial that's in there. So if I'm going to factor that, it would factor into 2 binomials. Notice I keep my 2 on the outside there. And then for 4x squared, there's really 2x and 2x, or 4x and 1. The one that's going to work though is 2x and 2x, because you'll see in a second how this works out. I always try 2x and 2x first, unless I recognize it as a special case. And then factors of 1 are 1 and 1, but because they have to multiply to be positive 1, but the middle's got to be negative, that's how I know they're both minus. And again, the check would be the outside, which is negative 2x, inside negative 2x. If you add them together, you get negative 4x. So my answer is 2 times 2x, the quantity 2x minus 1 times the quantity 2x minus 1. So that binomial is repeated, which is fine. You can write it twice, or just, if you wanted to, you could write 2 times the quantity 2x minus 1 squared. So you could just write one binomial to the second power, or write them as 2 separate binomials. Up to you. 24, first going to check your greatest common factor, and there actually is one. So 3 divides 12 and 75. So I have 3 times the quantity 4x squared minus 25. And then here's kind of my thought process. If I have a binomial, it's got to be a difference of 2 squares, otherwise I can't factor it. Or it is if a trinomial, I would work through trying to build my 2 binomials. In this case, I have a binomial, and I'm going to notice that 4x squared is a perfect square and 25 is a perfect square. So if this factors, which it does, it should factor into 2x and 2x plus 5 and minus 5. It has to be the binomial almost the same, except for the sign in the middle is opposite, because when I multiply that out, it would make my middle term drop out. So that 3's got to be part of your final answer, and those 2 binomials, doesn't matter what order you write them in, but they have to be those 2 binomials. 25, it's a trinomial, so no common factor between n squared n and negative 42. So if it factors, it will factor into 2 binomials. And when the coefficient of the squared term is just 1, then you could go straight to the variable times itself. And then I'm looking for factors of negative 42, so multiply to negative 42, add to negative 1. That has to be minus 7, positive 6. And that would be your factoring. You can check your outside inside, but that's the only combination that will work there. Number 26, first check for greatest common factor. 2, 5, and 3 don't have any factors in common. So if this factors, it will factor into 2 binomials. You'll notice, obviously, hopefully you're noticing a pattern is the steps that I'm asking myself as I approach each problem, because it really is a good way to think about the different types of problems you can come across. Again, trinomial will factor into 2 binomials. Looking to what multiplies to 2x squared, it's got to be 2x and x. And then I need factors of 3 that would make my outside-inside product add to negative 5. So I do 3 here and 1 there. Here's how I know this works. If I did my outside product, that would be negative 6x, 2x times negative 3, and my inside product should be plus x. If I add those together, I get negative 5x, which is my middle term. Therefore, that factorization is correct. Number 27, first look for a greatest common factor. 20, 7, and 6. No common factors, x squared, xy, and y squared. Not all three of them share the same variable. So if it factors, it'll factor into two binomials. The only difference in this one is we have x's and y's. So my binomials should have x's and y's in them. So for 20x squared, however, there's a few different combinations. Could be 20 and 1, 20x and x, 10x and 2x, or 5x and 4x. I usually try 5x and 4x first, and then kind of work my way out from them. So I think of the middle factor pair. So 20, 5, and 4 is, kind of the middle, I consider it. And then if I couldn't find a combination that worked, then I would try 10 and 2. If I didn't find a combination that worked, I would try 20 and 1. That's not necessarily a rule to follow. It's just kind of how I approach them. It's served me well in the past. So starting with 5 and 4 tends to be a good place to start. Unless it's blatantly obvious that I need 20x and x, I'm going to try 5 and 4. So then I know I need product of my last term. That would make the outside inside add to the middle. The one thing that I do have to consider is the last term of each binomial should have y's on them because they have to multiply to be y squared. And let's see if 3 and 2 in this specific spot works. So I'm going to try 5x plus 2y, 4x minus 3y. If I check my outside product, I would get negative 15xy. And if I check my inside product, I'd get positive 8xy, which adds to negative 7xy, which tells me those factors are correct. And then 28, first check for a greatest common factor. 4, 12, and 9 do not share any. So if this trinomial factors, it'll factor into two binomials. 4x squared and can be written with 4x and x, or 2x and 2x. I'm usually going to try 2x and 2x. You may or may not recognize this as a perfect square trinomial, meaning the first term is a perfect square and the last term is a perfect square. If you did, then that should streamline your factoring. If not, that's okay. Let's try factors that multiply to be 3. That would make the outside inside add to 12. So if I try plus 3 and plus 3, my outside would be 6x, my inside would be 6x. Therefore, those would add to the middle term I need. So 2x plus 3 and 2x plus 3 are my factors for number 28. Then the last few problems, still factoring, kind of walking through the same process. Greatest common factor. If yes, do that. If no, or after you've done that, check if it's a binomial or trinomial and kind of work your way through that. So number 29, check for greatest common factor. 9x squared and 100y squared, no common factors. But I'm dealing with a binomial, so I'm going to check if this is a difference of two squares. So 9x squared is a perfect square. 100 is, and y squared is. Therefore, we're dealing with a difference of two squares. So if it factors, it should be into two binomials that are only different by the plus or minus in between them. So how you build the binomials in a difference of squares is whatever squared gives you 9, which is 3, and whatever squared gives you x squared, which is x, so 3x and 3x. And then whatever squared gives you 100, which is 10, and whatever squared gives you y, which is y squared, which is y. So 10y and 10y, and one of them is plus and one of them is minus. If you multiplied them out, the reason why they have a different sign in the middle of each binomial is it would make the middle term, quote-unquote middle term, drop out, leaving me with just 9x squared and negative 100y squared. So you can check that multiplication if you want, but that is a difference of two squares, and the factor is exactly like that. Number 30, first check for greatest common factor. 10, 15, and 25 actually do all divide by 5. As far to factor 5 out of each term, here's what I would have left. And then I'm going to look to see if that trinomial factors into two binomials. So what I'd write is 5. And then I'm going to write two empty binomials and think about how to set them up. First term has to multiply to be 2x squared, so it's got to be 2x and x. And then I need factors of 5 that would make my outside-inside product add to the middle. So actually factors of negative 5, so one's got to be positive, one's got to be negative. The combination that'll work, though, is 2x minus 5 and x plus 1. The reason I know that works is my outside product would be positive 2x, and my inside would be negative 5x, and those would add to negative 3. Therefore, that pair of binomials works. And remember that 5 that you factored out originally, we're not dividing it so that it goes away. We're pulling it out front so that what's left is something that's simpler to factor. 31, check for a greatest common factor. 2, 28, 96 actually all divide by 2. So I'm left with x squared minus 14x plus 48. And then I'm looking to factor that into two binomials because it is a trinomial. So it should be x and x at the beginning. And then I need factors of positive 48 that add to negative 14. So then multiply to be positive but add to be negative. It's only possible if they're both negative, and it's got to be 8 and 6, because 8 and 6 add to 14. 8 times 6 is 48. And then the last problem here, check for greatest common factor. There isn't one. We're not dealing with a binomial, so it's a trinomial that, if it factors, should factor into two binomials. So I need factors of 8 that add to 7. The common mistake is we think, oh, factors of 7 that add to 8, but we're looking for factors of the third term that add to the middle term, and there aren't any. So if you think, we try 4 and 2. If we try 8 and 1, 4 times 2 is 8, but 4 plus 2 is 6. 8 times 1 is 8, but 8 plus 1 is 9. Neither of those factor pairs work if I check my outside-inside. Therefore, we would say this is not factorable, or sometimes called prime. I would accept either of those. So it is possible that an expression doesn't factor. This is one of them. There are no factors of 8 that would add to 7, so that would be it.